I'm Martin Divocký. I'm working at Highlights and I'm responsible for development of high energy laser systems. We are operating a laser bivoy or dipole, which we received in year 2016, and in that year we have reached 1 kilowatt of average power. 4 years later, we have increased the average power to almost 1.5 kilowatts, but unfortunately we couldn't use the bivoy laser in experiments because it was not protected from the light reflected from the experiments. And this protection is usually done by Faraday isolator, but Faraday isolator for 1 kilowatt of average power did not exist. My colleagues started development of such Faraday isolator in year 2016, and this year they finished the development and they will present some very exciting results.
My name is Ondřej Slezák. I'm the leader of the laser modeling team here at the Highlight Center, and I was in charge of the development of the Faraday isolator for bivoy laser. Small-scale Faraday isolators are relatively common devices which can be bought from several companies all around the world. But our device is quite unique in the sense that it's relatively big one and can handle the beam of bivoy laser. The device have to withstand such energy fluences and has to be able to provide the sufficient so-called isolation ratio. This ratio for our isolator is around 30 decibels, which means that just 1/1000 part of the energy leaks through the isolator in the, let's say, closed direction.
Hello, my name is David Vojna and I'm a PhD student here at Highlights. I was in charge of the design of the Faraday isolator and all of the work that was corresponding to its building and testing. We are standing here next to the superconductive magnet that is providing the magnetic field for the Faraday isolator. The magnetic field inside the magnet's bore is tunable by the electric current, and the maximum field that is able to deliver this system is 3.5 Tesla. The laser beam at this point of the bivoy laser is fairly large. It's 59 by 59 millimeters to be exact, and hence all of the optics needs to be large enough to accommodate this kind of a large beam. All of the needed optomechanical components and holders for this optics we needed to design here at Highlights. The most challenging part of the design was the development of the optomechanical holder for the magneto-optical components, which needs to be installed inside the magnet's bore. These magneto-optical components are made of terbium gallium garnet crystal, and apart from their proper alignment inside the magnet's bore, the holder needs to provide the sufficient cooling to compensate for the thermo-optical effects. So once all of the optics is aligned in the isolator, we needed to tune the magnetic field in order that the laser that would be propagating towards the experimental part would have maximum transmission, and at the same time any light that would be coming back needs to be maximally attenuated. This has been done by probing the isolator with a low power laser beam and testing this functionality for different orientations of the magnetic field and different values of its applied strength. Once we find the proper working point for this tuning of the magnetic field, it is ready for high energy testing with the bivoy laser. The maximum transmission towards the experimental part was 85%, and maximum attenuation for any light that would be coming back was 30 decibels, which corresponds to the attenuation to the 1000. In case you would be interested in more detail regarding the design and testing of the isolator, all of this is covered in the recently published paper that is available on our social media.